Okay, guys, we are going to do lab 2, and I have never done this before, but I think this would work. I'm making a video of lab 2, and you can watch this video before you come to our lab, and also after our lab, when you write your lab report, you can also come back to this video. So this will help you a lot with your calculation. This is very important information in this video. So in this lab 2, we will use a metal to react with the EDTA. The EDTA goes to the burette. It's a titration. So in the end, we get a complex. This complex metal ligand complex is a chelation, and in this case, we first assume we use the 6 μ of EDTA, but you use your real data. After this lab is done, you should have your own data. Here we assume we use 6 μ, and we also assume the starting point after the titration is done, everything is gone, the reagents. We start from the product, the complex. It goes this direction. It's a reversible reaction. We assume we start from the complex, and here the starting concentration of the complex is mole divided by 56. Remember, this 6 is, we assume it's 6. You use your real number after you are done with your lab. So 50 plus 6, 56, and the mole. How do we get this mole? We get this mole from this metal. It's 1-to-1 ratio. It's 1-to-1 ratio. We measure around 0.1 gram. Around, it's not 0.1 is not an exact number. Around this number, 0.1 gram, and this number divided by molar mass. Molar mass, remember, it's a sulfate salt, and also it has water molecules in it in its hydrated form. And then you mass divided by molar mass, you get the mole, and then you use the same mole as the complex. Mole divided by volume, you get the molarity. You do the calculation conversion, and you get the molarity. And this is a starting concentration. This is an ICE table. ICE table, you should be very familiar with this by now because you have taken general chemistry, right? So this is ICE table. Initial, change, and equilibrium. Initial is this. The change is x minus x. Let's assume x amount of this complex decreases by this amount because it breaks down to the reagents. It goes to this direction. It goes in this direction. And in the end, when it's in equilibrium, it should be starting minus change here. Okay, now this is the key part. This x, we assume it's like too small. It's a very small number. So when we do the calculation, because we are not living in an ideal world. If we did live in an ideal world, we take x into consideration, and also I'd be able to sing like Elvis. But this is not an ideal world, so we ignore this x because it's too small. We make this assumption it's too small. We ignore this part. So when it's in equilibrium, it's the same as this, the concentration. And we use n to represent this part, is concentration. When it's equilibrium, we use n. So this part is n, and also we are calculating kf. This kf, not this kf. This is kf prime. This one and this one the same, kf prime. We want kf. In the end, it's here. We want this kf value. So how to do that? So I made it a lot easier because this is just nx squared and a fraction, this alpha thing. So we just mentioned how we could calculate this n, and how do we get x squared? X squared, by definition, kf, formation constant, by definition is like this. The complex divided by the two the product of the two reagents. This times this. We use x to represent the concentration of this and this. So it's x times x. We get x squared. We have n. We already have n. We know how to calculate n, and we want x squared because it's here x squared. We want n. We want x squared. We also want this alpha, this fraction. So this kf prime is in a table. We can find kf prime. It's not pH dependent. Which table? How do we find this kf prime? Is here. In this table, you can pause this video when you watch this video. You find the kf value. The metal ions are all here. So you need to do conversion because this is log, and you'll find the values you want in this table, and you go back. You go back and you plug the value in this formula. Here you have the kf prime. You have n. You can get this x squared. Then you have n. You have x squared. So you have n. You have x squared here. You just need one more thing. This is the alpha fraction, this thingy. So it's in this table. After you are done with your titration, you measure the pH of the solution. We do some roundup here. We need to do some roundup here. If let's say you get the pH you measured is the 5.4, so you just use a 5. You round it up to 5. If it's a 5.5, you round it up to 6. You use a 6. Okay, you round it up, and then you get this alpha y4 minus this thingy, this fraction thingy here. It depends on what pH you get in the end. Okay, so you can find this alpha thingy here in this table. Now let's go back. You have this in that table. You calculate x squared. You have n from here. You should be able to calculate kf. This is very important in your post-lab report. And when you answer the questions, you just need to answer the questions. You don't need to make it a formal lab report for this lab. So you do not need to write down the background, analysis, discussion. No. You don't need those sections for this lab. All right. Good luck. We'll see you in our lab. If you have any questions, email me at any time. Remember, email me. Do not send me Canvas messages. Use email, and also tell me your name and your section number, because I don't just teach one section. Include your name and section number. All right, boys and girls, and I will see you in our lab. And take care.